Next, we have Rana Adhikari, Caltech Professor of Physics.
Okay, I mean, you've heard all about the background now, so I'm going to give this is kind of unusual talk. This is not going to be a normal scientific talk because this is not that kind of event. And I'll warn you, this will be more like it's like family vacation photos. That's kind of what you're here for. So yeah, as you've heard, there's these 4 different LIGO sites in the LIGO laboratory and the 2 observatories and what we're doing. And I'm going to give you a little bit of my personal journey through this time. So this is a shot of the LIGO interferometers, or one of the LIGO interferometers, kind of diagrammatically. And as I go around the world, I find people ask me often questions like, how do you actually do it? And how do you make that measurement? And what's going on? How is it possible that you can measure anything that small? And there's a bunch of things that get in the way of making this measurement, but we also have a bunch of solutions for what to do about it. So the main thing you might think about is, well, the mirrors move too much. You're hearing about motions of proton size or subatomic size, and you have mirrors which are made out of atoms. And how do you actually measure something that's a million times smaller than an atom when you have things made of atoms? Anyway, that's why I thought I was going to get out of this field earlier, because I thought that sounds like a bogus idea. Turns out to be not that bogus. For seismic vibration, and excuse my animations, for seismic vibrations, we have a sophisticated seismic isolation system. So through a combination of active and passive vibration isolation stages, we filter out all of the ground motion. So by the time we get done with this multi-stage system, which is built by hundreds and hundreds of people, the amount of motion you get at the final point where the actual mirror sits is something like 1 billion times less than the ground motion. So it's an incredible factor that we get, and that's the result of, I don't know how many years of vibration isolation work, but I've only been involved with it since maybe the late 90s, and since that time, it's already improved by a factor of 1 million. Another major problem that we have is so-called residual gas. So if you're shooting a laser beam all over the desert or in the swamps of Louisiana, there's a problem, which is if you shoot a laser beam like this and the gas is in the way, then the laser beam scintillates. You see the beam kind of jittering around and fluctuating. And so for that, you have to get rid of all this gas. And let's see how this animation works. So you get rid of some of the gas. How do we get rid of the gas? Let's try again. Yes. We have a huge vacuum system. So the entire LIGO system is sort of a 8,000 meter L-shaped tube, and it's completely evacuated of gas. It takes a little bit longer to pump than you might think. And that 8,000 meter thing is the equivalent of 300,000 kegs of beer, as I've computed. And I think that if you're not familiar with the metric system, that is what really brings it home to you. It's a lot of beer you could fit. And it looks like that. But we also have this problem that we have mirrors, and like I said, they're made of atoms. And what to do about it? Well, over the decades, luckily we have this magical material which is called glass. And glass has a lot of amazing properties that allows us to actually use this as a mirror. And so it's a combination of atomically flat mirrors like this, meaning really if you look at the surface, the perturbation from a flat surface or a curved surface is at the scale of the hydrogen atom when you go across the whole surface. And just think about it. It's something like 10 to the 20 atoms on the surface. So the polishing and coating has to be this good that you get down. I think I'm laughing at myself when I'm talking about this, but it used to be when I started, I would say, can you imagine the mirrors are smooth down to the level of hundreds of atoms? And that was sort of the wow factor. But every time I give this talk, it's kind of been, it keeps getting better. And so I can't use any old slides anymore that say it's hundreds of atoms or something. It's really down to the angstrom level. And they're made of this super ultra pure glass on the surface and glass also inside the bulk. And that kind of answers the question for how you can make the measurement, that almost all of the thermal vibration of the mass is happening at a few discrete frequencies. And so the mirror is sitting around thermodynamically singing at a few different tones. And if you listen to the LIGO detector just with a audio file in your phone or something like that, you'll hear all the vibrations of all the different pieces just singing along. And it sounds kind of beautiful if you're into that kind of thing. As Kip said, we also have this problem that you actually have the quantum mechanical fluctuations of the laser light or of actually empty space that are perturbing the system. And the main way that is that you have this thing called shot noise, which is quantum mechanically, there's the individual photons arriving at your detector. And so when you're listening for this gravitational wave signal, which you hope is a beautiful kind of chirp, the problem is that there's a hiss in the system. And you can think about this like a microphone, and you're listening to this beautiful audio symphony of the universe, or you wish you were, but instead you just get this hiss. And for all of the time that I've been in this field, I would say most of the time, it's just kind of that. And the reason I'm talking about this is that up until 2015, there was nothing. And for me, that felt like a long slog. But that whole time, we were just listening to the detector and not any kind of signals. And so we got to be really, I don't know, you try to make fun out of what you got. And so this is what we had at the time. And so that's been kind of solved now through this idea of squeezed light, which is really squeezing the fluctuations of empty space itself, which sounds like a kind of science fiction thing, but it's been pulled from the 21st century. Well, maybe we are in the 21st century. So it's been pulled into the 21st century by the 21st century. And I thought, well, that's pretty good. We've done that part, and now it's getting better. It turns out that was not even enough. And so an extra cavity was added to the system, which allows us to manipulate this squeeze light and even get rid of the fact that the individual photons are perturbing the mirrors and shaking the mirrors around. And finally, that thing's been squashed. And now what do we have left? Well, most of the fundamental things have been gotten rid of, and now we're working on the next order of smaller things. But I wanted to mention this fact that when you look at that previous graphic, I'm talking about the big, high-profile problems that we have, that there's atomic fluctuations or quantum fluctuations or gravity of the Earth and those kinds of things. And we can go on and on about those things, but there's a lot more to how the actual experiment's done. And that's, I think, in things that we don't really talk about that often. Of course, there's a huge amount of computing that goes into actually looking through these enormous amounts of data and finding the signals we're looking for. And that kind of, if you're not involved in that task, it's kind of hard to explain what's the magnitude of that. But you have incredible amounts of data, and up until the first detection in 2015, we don't really know what we're searching for. We have theoretical predictions for what might happen, and then you kind of search for everything out there. And it's a kind of baked into the character of this field that for decades and decades, we had nothing and no signals to look for. And how do you look for something when you don't know what's out there in the universe? It's really a search for the unknown. And so the first signal that we got was a great gift because, in my opinion, it was the cleanest signal we could get. It was two black holes, which are about the same. They're not spinning too much, and they collided, and the signal was extremely strong. And it happened as soon as the detectors were turned on. And the character of the signal was such that the main energy release of the black hole merger happened in the most sensitive band of our detector. So I would say, we should celebrate nature for giving us the best gravitational wave signal we could have gotten for the first one. I have to admit, I thought it was fake for about a month because it just seemed, if you see a squiggle like that and you've been seeing people, give you equations for all of your life and say, this is what it's going to look like. I mean, we're really, how often do people predict things and they're actually correct? So I thought there's no way when the two black holes merge that we'll just see a little squiggle like this, but some kind of surprising, magical thing will happen, or relativity will be overturned in that day or something like that. And it didn't. So I didn't believe it because I thought it was just something that someone had calculated and stuck into the data stream. But anyway, we were eventually convinced. And behind the scenes of all this computing and analysis, there's a whole substructure to the LIGO experiment, and I find, I'm sitting here on campus in the heart of the LIGO laboratory, and I kind of get used to the impossible because it's just happening all the time, and you wander around the labs and you see what's going on, and someone will say, today I used 1,000 computers to do this kind of analysis, or someone's baking some sort of special element that happens to work in our system and make it all work. But when I go off campus and someone asks me, how do you guys actually build that thing so that it doesn't move that much? And it's kind of a fractal story where I say, well, we've got springs of this kind, or we have wires of this kind. And they say, how do you do that? And then kind of as I'm telling the story, just because I've been in it for so long, I remember the names and the faces of all the people who had to do all of that engineering work for decades and decades to get us to that point. But if you look at any of the pieces of the instrument with all of these people behind it working on it, every one of these elements has a story behind it of how all the pieces came together. And there's a long history of people struggling to get it to work, and it doesn't work. And it's a tough slog, I have to say. You're in the lab day after day, and you're working on your little thing, and what's the encouragement? How do you actually keep going when nothing's actually working out for you for so long? And for me, I've been involved, before the first detection for about 15 to 20 years, but there's, already when I got to Caltech, there have been people doing it for decades, and I couldn't understand how they kept going after all that, I wouldn't say lack of success, but kind of a tough slog with no big rewards. But you can see the progress over time. We had one event back in the beginning during our first observation run, and people kept tweaking the detector and making improvements at all 4 of the LIGO lab sites, but also within the international collaboration. And the rate greatly improved for our second observation run, and we found a few more black holes. This is mostly black hole detections versus time. And then we got into our third observing run, and you can see this uptick all of a sudden, that the number of signals we were getting per time dramatically improved. And then just recently in our last observing run, a huge rate increase. And what's going on there? It's not like the universe is all of a sudden merging a lot more black holes because it likes us. The universe doesn't seem to care about us that much. This is all of the people behind the scenes who are making this happen, going through and whittling down every little annoying part of noise that's getting in the way. And as they do it, you see, and you can see it in some of the posters that are outside, that now the same kind of signals from space, when they come in, previously it was kind of listening to a scratchy gramophone record from the 1900s. And now when we're listening to the gravitational waves, it's like a high fidelity instrument. It's amazing to me, starting off from the viewpoint where we had nothing happening and you would wait for years and get no signals. And now there are some days where if you're sitting in the control room of the LIGO detector, you might get 2 black hole mergers in the same day. And that just seems like such a fanciful thing to even worry about. What happens if we get 2 black holes at the same time? Won't we get confused? I mean, it's like saying, what if you win 2 lottery tickets in the same day or something? What's the chances of that? We're kind of getting into that stage now where it used to be, imagine this, your eyes are closed, and you're sitting in a dark room, and you hear one whoop after 50 years of searching. And that's the only information you have about the dark universe. And then a few months later, you get another one, and you get another one. And we're kind of getting to the point now where every day you might get a little bit of a whoop. And so you're starting to picture really what's going on in the universe beyond what you can tell with telescopes, beyond just looking out there. You're now hearing what's going on in the universe and getting a different picture. And that's kind of my hope for this field, that every year, that curve will tilt up and up. And we're filling in this dark picture of the universe and what's really going on. So mostly I've been telling you about the hardware, but I'm a convert to this. I'm really a hardware person, but in recent years, I've realized that probably the most important part of this whole enterprise is the software behind the scenes that actually runs it. This is the family photos part of the talk. I got my start with Dave Wrightsey back in 1996 because I was looking for a part-time job while I was at the University of Florida, and I was working at a gas station, which paid more than LIGO paid me, by the way. But I thought this is a safer opportunity because there's no chance of getting run over or anything like that. And so I took this job, and I thought I was going to be cleaning test tubes and things like that. And he said, no, we have this project, which is the Laser Interferometer Gravitational Wave Observatory. And I thought, wow, I've got my interview coming up on Monday. What should I do to prepare? So I read A Brief History of Time by Stephen Hawking, because I thought Dave was going to ask me a lot of deep questions about the universe. And I went in there, and I gave them this spiel about how the universe works, and it was an exciting book I had read. And he said, that's great, but we don't do anything with that. And get here in the lab, and I want you to move these boxes from over there to over there. And I'll pay you $4 an hour. And I thought that was a good deal, so I took it. And he gave me a raise when the minimum wage went up in the state. So thanks for that. And after a couple of years, I moved to MIT. And this is a picture of the group in 2016. It's a lot more modern. I spent a lot of time in this lab working on some of the first pieces, pre-prototypes of LIGO. But I have to say, and Ray was there at the time, but he said, I'm too old. This was in 1998. He said, I'm too old, you shouldn't work with me, I'm kind of a has-been. But you should work with some of these younger guys like Peter Fritschel and David Shoemaker, Mike Zucker. They know what's up. And you should get into this, start helping us build the LIGO detectors. And so they set me to work. And I just didn't understand it was my first year as a grad student, and I had no idea why they were telling me to do certain things, like go work on this camera, go work on that detector, go do this thing. I don't know. I thought it was a lot of grunt work at the time. And I thought, this is probably not for me. I need to get out of this field. It's doomed. And so I went to talk to Ray, and I said, I don't like any of this stuff that I'm doing. I want to do something that's more scientifically relevant. And he said, all right, well, you seem like a moody kind of person, but let's see if we can satisfy you. So for my summer break, he sent me to, spring break, he sent me to LIGO Hanford. And I got to LIGO Hanford, and this is a picture of the Hanford staff in 2016. And it was much smaller back then, but it was amazing. I arrived, and immediately they said, you seem like a smart guy. We need someone to clean up all these rags around the vacuum chambers and mop up and carry around some aluminum foil for when we're working in the vacuum system. And I thought, this is a lot of fun. I get to run around and do whatever I'm doing, and every day as I do something better, they give me a more and more important job. And so I came back to MIT and I said, I would like to work on this LIGO project. This seems like a lot of fun. And so Ray sent me there for the summer. And we worked and worked in the vacuum system for a couple of months, and we got the first laser beam resonating in one of the LIGO systems. And I remember on that day, we got it to work after months and months of work. And someone at the observatory gave me a key to get into the observatory that day. And I felt like they were saying, nice job, now you can, you're allowed to come into this place. But I think the thing about this place, and it's because of all of these people, but then also Stan Whitcomb, who you heard about, who said the initial mood in the place, it was so supportive. As a first-year grad student, and I'm thinking about whether or not I want to be in this field, the entire staff would ask me all the time, how's it going? And is the laser going well? And what are you doing? And it was this feeling that, you're at this remote place in the desert, but there's something like 40 people there who are really interested in your success. And I found that to be, it's like such a unique experience in my life that I thought, I've got to stay in this field. This is just a lot of fun. And they'd let me do whatever I want. So I thought, that's really the place to be. So I went back to MIT and I said, I've decided not to quit LIGO. And Ray said, whatever, I didn't even know. But I said, I love the Hanford staff. I'd love to go there and I'll do my PhD there. And he said, well, I don't care what you think, but I'm moving to Louisiana and you've got to come with me. And I said, I don't know. I don't really want to go back to the South. And he said, I don't care what you think. You're coming. So we went down there. And I got to Livingston, and that was a tough place to work in when I first got there. There was a lot of, I'll just say there were a lot of feelings going on at the time. But the same thing happened to me that happened at Hanford. I started working there, and after a few months, I could just tell that the staff, and mainly I would say the younger staff who are like me, they're not so young anymore, but they were behind me from the first month or so. And there was many, many late nights where it was me, Ray, and then some of these younger younger staff after midnight sitting around, and really, this is the early 2000s, and nothing is working. Like the laser's pointing off, electronics are exploding, there's animals all over the system. That it's nothing like black holes and quantum mechanics. It's just a lot of dirty drudgery, it felt like at the time. But because of people like Stan Whitcomb and Ray Weiss, I got a chance to really get my hands on the LIGO detectors at the time. And because Ray had retired by that time, it wasn't like a typical grad student advisor role where the professor sort of says, go off and do these things. It was the two of us hand in hand working on things. And we spent a lot of days and nights traveling around Louisiana, getting sandwiches and having conversations about what to do. And because of that, I really got my start in this field, I think. And so I thank the LIGO Livingston staff for giving me this huge amount of freedom and support, and it continues on to these days for 20 years. So I went back, I finished up my thesis, and then I thought, we haven't found anything. And I was promised when I joined grad school that there would be a black hole detection by the time I graduated. And I had a thesis title all set out, which was going to be the first discovery. And I didn't find anything, so I thought, and maybe you get a pattern. I thought, no, I've had enough. It's time to quit. And I'm gonna leave this field, and I'm gonna go into some field which is much more promising, like the cosmic microwave background, because they're about to find gravitational waves any day now. And so I should work in that area. So I was all set to leave MIT and go to some other place. And then Alan Weinstein contacted me. He was told not to. He was told, leave Rana alone. He's gone crazy. He's going to leave this field. And Alan ignored everyone's advice and contacted me anyway and said, maybe you should come here because there's a prize postdoctoral fellowship you could apply for. And I applied for that and was completely rejected. And I thought, I tried to come here for grad school, and I think Alan was on the committee and rejected me then. And then I applied for this postdoctoral fellowship. I was again rejected. And Alan said, you could just come here as a regular postdoc, and we'll treat you nicely. So I came here to Caltech. And although I had been to these other sites and gotten all kinds of support, I came to Caltech, and I think Barry was my supervisor at the time, but Alan was actually, maybe my more formal supervisor, and there was no constraints. I thought it was the most amazing place because I got here, and Alan said, you should just sniff around and figure out what you want to do and do it. And over my time here, even though we didn't have any signals back then, this was 2004, and for the next 10 years we didn't have anything, but even while I was working away in the labs and people in my group were working away trying to make it happen, we really didn't know when the first signal would come in. I didn't believe that we would turn on the advanced LIGO detectors and immediately start working. So I thought, I don't know, it's been decades now we're in this area. Is this what my life is going to be like? Just measuring nothing and just listening to the detector hissing all the time, and it's all about noise and noise and noise. But people on the faculty would come by once in a while under some kind of pretense and kind of just chit-chat for a while, and then on the way out they would say, Rana, by the way, I don't care what anyone else says about you. I believe in you. I think you can do it. And multiple people said that, and I thought, what is the rumor going around on campus that they don't believe? But, being here this entire time has made me, really appreciate what it takes to make this kind of thing work, which is you got to have a group like this which works cohesively, and it's not all about black holes and quantum mechanics all the time. Every single piece of the LIGO detector, when you look at it, like I was saying, there's a whole tree of story behind it, and how do you actually get it to go? And it's from, the people who think about black holes all the way to people who are building the facilities and making sure that the lights are on every day and that animals are not creeping into the system and whatever it takes. But it's a massive, massive operation that takes all of these hundreds of people. And I think the thing that I find remarkable about the people is that among you all, you have that force of willpower and inspiration to keep it all going. And the fact that it's been going for decades is amazing. Yeah, so I want to say something about my PhD advisor, Ray Weiss. So I got into this field, and it was probably, yeah, as I say, the late 90s. This is a picture of his office. And when I got into grad school, I mean, talk about being like a little fish in a big pond. But I always thought I was really smart, but then I got to grad school and I realized everyone else thinks that they're really smart too. And I'm not all that smart. And I had a lot of trouble with how tough the school was. And Ray said to me, you know, it looks like you're struggling. I'm not sure if you're going to make it. They might kick you out of grad school. So why don't you come to my office this Saturday morning and we'll see what we can do. And it began a whole series of Saturday morning weekends that everybody in his group who knows about this would call it reform school. And it was basically like if you didn't have your, you know, electromagnetism and quantum mechanics and really down, you'd have to show up at his office at 9 a.m. and you'd go to this chalkboard and he would sit back. And by the time I arrived, he had stopped smoking his pipe, but he would still hold a pipe in his mouth. And I would do some equations on the board, and he would say, it's interesting that you thought that that's the way to do that. Now explain to me why you did that. And it would go on and on like this. And you know, through this experience of hours and hours of Saturday morning reform school, I finally passed my exams and got through grad school. And my whole experience with him was like this, that he would take people, and it wasn't just me, but anybody he'd encounter, and he'd really care about people and would take them along and make sure that if you're having trouble, he would figure out whatever it took to get you to the next spot. And he did this, I thought it was just for me, but then I later found out it was for, you know, like multiple generations of grad students. And we worked hand in hand for a few years in Louisiana, but after I graduated, it's like having having an uncle that never let you go. And basically the advisor relationship never ended. I thought it was going to be over in '04, but for the next couple of decades, he kept poking his nose into my business, whether I wanted to or not. And one of the major problems he would say is, why aren't you married? And over the years, a lot of the times when I was trying to talk to him about science, he was trying to set me up with somebody and say, what about her? What about her? And I'd say, no, Ray, I'm focused here on the science. And so a couple of years ago, Akanksha, my now wife, not wife at the time, I said, hey, Ray, I'd like you to meet this girl I'm dating. What do you think? And he said, how about this? Why don't you come to Maine, where we go on vacation, and you join us there? And I said, I don't know if this, that seems like a big gamble. How's it going to go? But I never regret it. So we spent the last few years vacationing in Maine with him, and we've had a lot of long conversations about science and people. And the thing that I was amazed by when I went there is that his influence in this island in Maine was a lot like I would see it at MIT or in Louisiana, that the way he would go around and talk to people in the shops and just locals there, you know, he was helping people there, people with their kids and their grandkids and their schooling. And he was just that kind of person whose main priority was people. And he said to me, even just a year ago, he said, you know, you've only got a finite resource, and what are you going to do with your time, and what are you going to do with your money? And I said, I don't know. Why are you asking me that question? He said, this is it. The best bet is always to put it into young people. He said, no matter what you've got, that's always the best return on investment that you can do. And so I felt strongly that that's the right thing to do. And I thought it's a good reason to be at Caltech, because we have students here who are bright and they're enthusiastic. And putting our resources into them is one of the best things that we can do. So that's all fine. You know, we've detected signals and so on, so that's great. But you might want to know what's happening next. We have a number of upgrades planned for the LIGO detectors, both in the coming few years and then in the coming decades. And that includes improving the technology in the current detectors, as well as building more advanced detectors in the future, which will really take us to the edge of the universe. And there's just some pictures here I wanted to show you. There's improved quantum squeezing coming in the future, improved optics so that we can use more laser power and see further into the universe. And then finally, the use of AI for control of the interferometers and design of experimental systems. So these are new adventures we're just getting started with. And they're speculative, but I would say, as you heard from Kip and you've heard from others, it's a time to be bold, because you can keep on doing what we're doing and do more of the same. But what I've always seen from this group and the groups at the other observatory sites is that when we're bold, not everything pays off, and that's okay. But you've got to go out there and be risky and try out things that you think are not going to work out. And I think, you look at what Kip said about 1980 and the resources that Caltech put into this. I would have said, I would not have put my money into this back then. I would have said extremely, extremely speculative proposal, but it really, really paid off. And if we don't do it at a place like this, then who else is going to do it? So these kinds of things, plus anything else you can dream of, you should put it on the table and say, Caltech is sort of a dream factory that generates dreams, but then turns them into reality. And this is a kind of, I think this is a kind of attitude that we already have, but we shouldn't forget that that's how this field got started. So one of the major things that's happening in this field is the addition of a third LIGO. So we have 2 in the US, and here's a plot of the, I've lost my laser power. That seems like a staged thing. I'll just point with my hand, and you can imagine the infrared laser beam. So it's a map of the world, and the numbers on there show you the time delays between the different LIGO sites. And so there's Hanford and Livingston there in the US, and there's the time delays to the Virgo site in Italy and to the Kagra site in Japan. And I is for India, which is the proposed site, is the site of the new Indian detector. So this is a picture of LIGO Livingston here in its remoteness in the forest, and LIGO Hanford out there. And this, artist's conception of the LIGO India detector, also similar in a remote area. Oh, okay. It seemed like a good idea at the time. Oh. All right. Nice. All right. I don't know what that adds. So with the LIGO India detector, we would finally be able to do this scientific thing, which is called triangulation. And I agreed to have no equations in this talk, so I'm not getting too technical. But remember, triangulation means 3. That's the key. And with 2 LIGOs, there's not much triangulation going on. So that's the main motivation for the LIGO India detector. Once we're able to have a third detector operating with the full LIGO sensitivity, we should be able to see further into the universe, get much more sources, but most importantly, tell you where the source is coming from and tell you the polarization, meaning, is the binary system rotating like this, or is it rotating like this? Is it face on or is it edge on? Things like that, and really find out more about the source. You may have seen, if you're, depending on where you parked on campus, that there's a new building being built, and this is the Ginsberg Center for Precision Quantum Measurement. It's kind of a mouthful. The lab is set to be built and ready to move in by the summer of next year, and we'll be moving a large portion of the LIGO labs into the basement, which you can't see here. But I have to tell you, they're for sure going to be the best laboratories that I've ever worked in. It's nothing against the labs that we have now. They're fine labs, but these will be I think the most highly engineered, lowest noise, and highest capability labs we're ever going to have. And the vision for that place is we're going to attack all of these pillars of quantum technology. So you know about quantum computing, you must have heard about it. People also have the idea to use quantum mechanical systems to simulate quantum materials. One of the limits of the precision of LIGO now is the vibrations of the mirrors that we have. And the idea of quantum materials is that we will be able to engineer from the atomic level what are the mirror surfaces and how to make them vibrate even less. And then finally, quantum measurement and quantum control, which is taking the idea of entangled light for doing more precise measurements, but ratcheting it up. not just having correlations between pairs of photons, but multiple photons and engineering really exotic quantum mechanical states, which sound like science fiction, but not to me anymore. I think it's like a science fact. And this is a update from this morning. You can see most of the floors are built up, and most importantly, the windows are on there. And I think it looks like a beautiful building. So I'll just conclude here by saying there's a lot to do in the world of gravitational waves, and we've just kind of gotten going. We have hundreds of signals. So if you compare that to the night sky, you can see if you're on a mountain or someplace where the sky is clear, there's a lot of stars in the universe, and it's billions and billions, as Carl Sagan would say. And what we've got now so far is hundreds and hundreds. And so the gap between hundreds and hundreds and billions is the adventure that we're on. And life is not just about binary black hole systems. We're turning on a microphone to the universe that no one on Earth in the history of humankind has turned on. And the loudest things that we've found so far are the black hole mergers and the neutron star mergers, but that's just the beginning. And in the next, after the break, we'll have a Q&A session next, but then after the break, you'll hear from 2 different panels which will really address this, what are the futuristic ideas, both on the side of astronomy and also on precision measurement. So I hope you stick around after the break, because the panels are where I think the real excitement will come from. Thank you for your attention.